Imagine sitting down on your sofa, and as you settle in, it subtly adjusts its firmness just for you. Maybe even nudges you slightly towards the person you're talking to.
Or picture a table that can, grow or shrink depending on who's using it. Not because you're pulling out leaves, but because the table itself knows and transforms.
Yeah, exactly. That's the kind of fascinating future hiding in the sources you've shared with us.
They really explore this profound shift, don't they? Moving furniture from just being static objects to becoming dynamic, intelligent, and really crucially sustainable systems, things that actively respond to us and the environment.
It's furniture that doesn't just sit there. It actually participates in the space, changing form, adapting, sensing what's going on, maybe even like influencing how we behave.
And precisely. And in this deep dive, we're going to unpack the key ideas that make this possible. We'll look at the materials, the sort of revolutionary building blocks, the principles behind giving furniture movement and shape-changing abilities, how we'll interact with these future objects, the really cutting-edge ways they'll be made.
And that sustainability link, too.
And how it all ties back to creating a more circular, sustainable future. That's critical.
So our mission here is to pull out the most important insights, the kind of aha moments from these sources, giving you a real shortcut to understanding this incredible transformation. Okay, let's dive in.
Let's do it.
So the first big idea these sources really hammer home is this fundamental shift. Furniture is, well, it's coming alive. It's moving way beyond just being a fixed, unchanging thing.
Exactly. The analysis really points out that our whole static view of furniture, it's being completely upended. And it's not just about, smart furniture in the typical IoT sense.
Right, like connected fridges?
Yeah, it's deeper. A paradigm shift driven by some incredible advancements in materials, science, robotics, and computational design.
And it feels like this is happening now because of some really pressing needs, right? Like we need spaces that can adapt fast, especially in cities where space is tight. My tiny apartment could definitely use a table that just vanishes when I don't need it.
Absolutely. There's that evolving user demand for adaptability, for space saving, but equally critical, and something these sources really emphasize, is driving a lot of this innovation, is the urgent global need for environmental sustainability. The traditional furniture industry, it creates a massive amount of waste.
Okay, so the push for this adaptable, intelligent stuff isn't just about cool features or convenience. It's also fundamentally about waste reduction and making things last longer.
Precisely. These pressures are pushing the vision for furniture away from passive objects towards these active, responsive systems that can, dynamically adapt, serve multiple purposes, and inherently last longer or be easier to recycle or reuse.
And making this vision a reality takes a real mix of different fields, doesn't it? Not just material scientists in a lab. You need computer people, engineers.
That's where that deep interdisciplinary convergence comes in. A breakthrough in a material that can change shape. It only becomes truly useful when you pair it with computational tools that can model and predict its complex behavior.
Right, figure out how it will actually bend or fold.
Exactly. And potentially robotics or integrated actuators to control that transformation in a useful way. It's a really complex interplay.
Speaking materials, the sources talk a lot about programmable matter. Now, that sounds like something straight out of sci-fi, but it seems to be the core building block here. What is it, fundamentally?
Yeah, it does sound futuristic, but programmable matter is basically materials engineered, so their physical properties, things like shape, size, color, texture, can be dynamically and reversibly altered.
Reversibly, so they can change back.
Yes, exactly. They change in response to some kind of external trigger, like heat, light, electricity, maybe magnetism.
So the potential for change is actually in the material itself.
Yes. Instead of relying only on external motors or complex mechanisms, the ability to transform is embedded within the material's structure and composition. MIT's self-assembly lab calls this true material robotics, or even...
I saw that phrase, robots without robots.
That's the one. It's a great way to think about it.
Robots without robots. What does that actually mean for, say, a chair or a table?
It means the intelligence and the capability for movement or transformation are in the material, not in separate, often bulky components. And this has huge implications. The sources suggest this approach could make self-transforming furniture much more cost-effective.
Oh, good.
Potentially comparable to traditional stuff, easier to fabricate, maybe shipped flat pack, and then prompted to self-assemble just by adding water or heat or something simple.
Wow, so the material itself does the assembly work.
That's the goal. It simplifies everything, design, manufacturing, logistics, by embedding the function directly into the material.
The sources mentioned a few specific types of these materials. It's not just one magic substance, is it?
No, not at all. And what's fascinating is the variety. You've got things like shape memory alloys, SMAs, like nitinol. These materials literally remember a shape.
Remember. How?
They're trained to return to a specific shape when heated, so you can bend them, deform them, and then apply heat, and they snap back to their original programmed form.
Okay, that's clever.
Then there are stimuli-responsive polymers, things like liquid crystalline elastomers, or LCEs.
LCEs. Those sound pretty complex.
They are, but they're really interesting. They're soft, flexible materials that can undergo really complex shape changes, twisting, bending, contracting, often powered just by light or heat. They're being looked at for soft robotics.
Like artificial muscles.
Exactly. Artificial muscles that could be integrated directly into furniture fabric or structures. The sources also mention shape memory polymers, SMPs, which work a bit differently but can also hold temporary shapes and return to a permanent one.
And it seems like nature is a huge source of inspiration here, right? Bio-mimicry keeps popping up.
Absolutely. Nature has spent millennia optimizing materials and structures for function and sustainability. It's not just copying shapes, though. It's understanding the underlying principles.
Like the lotus leaf.
The lotus effect, yeah. That's self-cleaning property. Sources mention furniture designs like a lot to US that actually use similar hydrophobic textiles or special paints so the furniture stays clean without harsh chemicals.
So learning from nature's clever designs, but it goes further, doesn't it? Actually using nature in the making process.
Yeah. Biofabrication, that's a huge potential area mentioned in the analysis. Using living systems like growing materials from mycelium, the root structure of mushrooms, to create lightweight, sustainable, biodegradable alternatives for things like acoustic panels or furniture parts. This ties directly back to that sustainability imperative we talked about.
You could literally grow parts of your furniture. That's incredible.
Yeah. It fundamentally shifts how we think about sourcing and making materials. It aligns perfectly with a circular economy. And nature gives us blueprints not just for materials, but for structural strength. Think spider webs, and even passive climate control, like designs inspired by termite mounds.
Okay, so we have these amazing materials that can change shape. How does that actually translate into furniture transforming? The sources describe different concepts for self-reconfigurable furniture.
Right. So on one end of the spectrum, you've got mechanical modularity. Think of something like the Qubit collection mentioned. It's tool-free, uses standard parts.
Like fancy Lego for furniture.
Kind of, yeah. But it relies on you doing the reassembling. It's practical, it's available now, and it inherently supports design for disassembly, which is great for circularity.
That makes sense. Simple building blocks.
Exactly. Then you move towards systems with more embedded intelligence, like robotic reconfiguration. The Roombots concept is a good example. These autonomous modules that can move around and connect to form different things.
So little robots building your furniture on demand.
Yeah, a stool becoming a chair, or chairs joining up to make a sofa all by themselves.
That definitely feels like the future.
And then you have things described as kinetic architectural systems, pieces like the Kirigami table or the commotion bench. These go beyond just changing function. They actively change shape in ways that can even influence how people interact in a space.
Okay, so the key difference is, are you assembling it? Mechanical. Are there little robots moving parts around? Robotic. Or is the material itself changing shape on command? Programmable matter.
Precisely. Programmable matter is that deepest level, embedding the ability to change right into the material. That's the robots without robots idea. And it's seen as really key to making this kind of dynamic furniture scalable and eventually cost-effective for mass adoption.
Why cost-effective? Seems complicated.
Because you're potentially reducing the need for lots of separate, complex, expensive electronics and motors. If the material does the work, it could simplify the whole system.
Got it. If the intelligence is cheaper and lighter because it's in the material, that opens things up.
It fundamentally alters the manufacturing and logistics, too.
Right. Let's talk more about the movement itself, kinetic furniture. How do you actually give furniture this dynamic ability?
Well, kinetic furniture isn't just, furniture on wheels. It's about designing form that can genuinely transform dynamically. It allows a single piece to serve multiple functions or adjust its shape to fit different needs or environments.
And those smart materials we just discussed are pretty essential for this, aren't they?
Yeah.
For the actual movement.
Absolutely. They provide the actuation, the ability to change shape or move in response to a signal, often without needing bulky motors everywhere. LCEs acting like those artificial muscles are one example. Or piezoelectric materials that change shape slightly when electricity is applied. They could enable subtle vibrations, maybe for feedback or damping unwanted movement.
Right.
The whole idea of material robotics is embedding that dynamic response directly.
So the material is kind of the engine, in a way.
It can be, yeah. But enabling and controlling all this complex movement, that takes serious computational power.
This is where computation gets really interesting, isn't it?
Indispensable. You simply can't design or predict how these materials will behave when they're dynamically changing shape without sophisticated computational tools. Things like parametric design.
Exactly.
It lets you define rules and parameters for how a structure should change or move. The sources mentioned the ollie chair, that folding chair, that relies on clever parametric design for its mechanism.
Ah, the chair that folds up really flat against the wall.
Yes.
Yeah.
And then there's finite element analysis, FEA or FEM. This is crucial for understanding how materials will behave under stress, for optimizing their form so they can transform efficiently, and for simulating the kind of complex deformation you need for soft robotics or intricate shape changes. It cuts down massively on needing physical prototypes.
So you can test it digitally first.
Loads of times. And simulation software lets you essentially program the material's expected behavior. You can simulate how different stimuli will affect these responsive materials and predict how they'll transform. Getting predictable, controlled movements is vital.
And then you need the control logic to actually make it all happen smoothly in the real world.
Right. Simpler systems might just use basic servo motors for precise adjustments, like changing a seat angle slightly, but more complex autonomous systems, like those Roombots, they need sophisticated algorithms, things like central pattern generators, CPGs, to figure out how to coordinate movement and reconfigure themselves effectively.
And that brings us back to that Whirlstools example you mentioned earlier. That's where the furniture wasn't just moving, its movement was doing something else, wasn't it?
This is where it gets really fascinating, and it connects kinetic design directly to user interaction. The Whirlstools subtly adjust their seat angles, just a small physical change, to encourage people sitting on them to turn and actually talk to each other. This is what the sources call adaptive affordance.
Adaptive affordance. So the furniture's kind of subtly guiding my behavior, nudging me.
Yes, exactly. It's providing soft steering rather than an explicit command. It really shows how kinetic properties can be used not just for function, but to influence social dynamics, and the user experience may be promoting collaboration, encouraging focus, or even providing a bit of privacy by changing shape.
That's a powerful idea. Moving beyond just changing form to using movement itself as a design tool to shape interactions.
It really is. Kinetic furniture isn't just about changing form, it's about influencing experience. And the sources are clear. None of this is possible without major strides in the computational tools happening alongside the material science breakthroughs.
That's a key expert insight highlighted, isn't it? Progress isn't just about finding a cool new smart material.
No, it's equally dependent on our ability to accurately model, simulate, and control the complex behaviors of these materials and the kinetic systems they enable. This demands truly interdisciplinary teams, material scientists, computer scientists, engineers, designers, all working together.
So investing in the digital tools, the software, is just as important as investing in the material labs.
Absolutely critical.
Okay, so we've got materials that can change, computation to control it, furniture that can move and even sort of steer our behavior. How do we actually interact with these intelligent objects in our daily lives?
Well, the overarching vision discussed is often called adaptive architecture spaces, and the furniture within them that physically transform and respond to us, ideally seamlessly. The goal is to minimize clunky interfaces, screens and buttons everywhere.
Right.
It aims for a synergy with the Internet of Things and AI, maybe even conversational AI playing a role.
But how does furniture talk to us or show its intentions without a screen or a voice assistant chiming in?
The sources mention this idea of architectonic gestures. It's about using spatial presence, physical form, and movement to convey meaning intuitively.
Gestures, like hand gestures.
Sort of, but with the whole object. Think about how the speed a door opens might feel welcoming or abrupt. Or maybe a chair subtly shifts its posture to kind of invite you to sit. These physical changes become a form of nonverbal communication, rooted in the object's function, making them feel natural. That adaptive affordance with the whirl stools is a perfect example of this physical communication.
Okay, so the furniture uses its physical being to communicate. How does it listen or sense what we might need or want?
That's where integrated sensor networks and smart materials acting as sensors come in. You have passive smart materials that just detect stimuli. Then active smart materials can both sense and react, creating a feedback loop.
Mm-hmm.
And then you get into what some sources call intelligent materials, which can adapt their behavior more autonomously, perhaps based on past interactions, a kind of material memory.
What kinds of things are these sensors actually picking up on?
Oh, all sorts. Environmental sensors measuring temperature, light levels, air quality. Biometric sensors could potentially pick up heart rate, body temperature, maybe even stress indicators through skin response.
Wow.
Potentially. Plus, motion sensors, chemical sensors, acoustic sensors, a whole suite of ways for the furniture and the space to perceive what's happening.
So the furniture could know if I'm feeling too warm or stressed out, or if there's annoying noise coming from outside.
That's the potential, yes.
Yeah.
And this data stream feeds into a larger IoT-driven system. Cloud platforms connect the furniture, the environmental sensors, maybe your own wearable devices,
Okay.
allowing for continuous monitoring and providing context-aware services.
Well, this is where the AI really kicks in.
Exactly. All this sensor data gets integrated, fused together, and then fed into AI and machine learning models. The sources even mention things like transformer-based models, similar to what powers large language models,
Right.
being used to process this complex data, understand the context, anticipate your needs, and then trigger the appropriate response. Maybe the chair adjusts its lumbar support, the lighting dings automatically, or a partition subtly extends for privacy.
So it's using AI to try and predict what I might want or need before I even ask for it.
Moving towards that kind of implicit anticipation, yes. The ultimate goal is for the interaction to feel as intuitive and natural as human-to-human communication, where we pick up on subtle cues and respond almost unconsciously. This needs whole new principles for human furniture interaction, focusing on these physical cues and predictive responses.
But this brings up a really important point that the sources do touch on. If my furniture is collecting all this data about my physical state, my environment, maybe even my stress levels, and potentially influencing my behavior, what about privacy and data security?
That's absolutely a critical question, and it's flagged in the analysis. The potential for continuous collection of really sensitive data within private spaces, your home, your office, creates significant ethical and security challenges.
Yeah, it really does.
These need robust solutions as the technology develops. How is that data stored? Who has access? How is it anonymized, if at all? How is it secured against breaches? These are huge questions that have to be addressed right alongside the technological development. We can't just build it and figure out the ethics later.
It sounds incredibly complex, too. Just the control systems needed to manage all that sensing, the data fusion, the AI processing, and then making the physical changes happen smoothly and safely.
It is. It's a major area of ongoing research and development, integrating all those diverse data streams, running the sophisticated AI models, and then executing precise physical transformations requires really advanced, scalable control system architectures. The level of intelligence and responsiveness you get is directly tied to how sophisticated those underlying systems are.
Okay, finally, let's talk about how all this amazing stuff is actually made. Traditional furniture manufacturing doesn't seem set up for programmable, kinetic, sensing furniture.
Right.
What kind of new processes are emerging?
Yeah, you need new ways of making things. One key process highlighted is 4D printing. Think of it as 3D printing, but with an added dimension. Time, yeah. You 3D print an object, and then later, over time, or when it's exposed to a specific trigger, like heat, water, light, it changes its shape or function automatically.
So you can print it flat, ship it easily, and then it just folds itself into a chair when you unpack it and add water.
That's the kind of potential it holds. The programming for that transformation isn't in a microchip. It's embedded directly in the material properties used, the geometry of the print, and the physics of the structure itself.
Wow.
This opens up amazing possibilities for things like flat pack shipping, reducing volume, and maybe even on-site transformation or self-assembly without needing tools or complicated instructions.
The intelligence for the transformation is literally baked into the print.
Exactly. Multi-material 3D printing is often key here, allowing different parts of an object to be made from materials that react differently to the same stimulus. Further out, looking even more towards the future, sources mention concepts like molecular assembly.
That sounds very nano.
It is rooted in nanotechnology. The idea is building structures with atomic precision, either designing molecules that will self-assemble into the shapes you want, or the even more distant vision using hypothetical nanoscale machines,
Like tiny robots.
sometimes called assemblers, to place atoms exactly where you want them. The idea of a molecular assembler or nanofactory that could fabricate almost anything, including complex furniture, atom by atom, is still very much on the theoretical frontier, but it's part of the long-term landscape being explored.
Definitely sounds like gazing far into the future. But all of this, the new materials, the kinetic abilities, the manufacturing, seems inherently tied back to that really pressing need we discussed right at the start, sustainability and the circular economy.
This is where it all comes together, and it's a crucial thread in the analysis. The traditional way we make and use furniture, that linear take, make, dispose model, is incredibly wasteful. Furniture is bulky, it's often made of mixed materials that are hard to recycle, and it gets thrown out way too quickly.
Yeah, think of all the cheap furniture that ends up on the curb after a year or two.
Exactly. The circular economy offers a completely different approach. Minimizing waste, maximizing the value we get from resources, and keeping products and materials in use for as long as possible through reuse, repair, recovery, and recycling.
And this new vision for furniture programmable kinetic seems almost purpose-built for that circular model, doesn't it?
It really aligns beautifully with core circular principles. Think about durability and modularity first. Designs that allow for easy repair or component replacement, like that qubit concept, again, extend the product's lifespan significantly.
Right.
And reconfigurability itself is a form of modularity. If your furniture can adapt to new needs or spaces without you having to buy completely new items, that directly reduces consumption and waste.
So my chair becomes a useful table when I need one, instead of me buying a table and either storing the chair somewhere, or worse, discarding it.
Precisely. Then there's the material choice itself. The push is towards using sustainable inputs, recycled materials, naturally fast-growing options like bamboo or cork, and especially those biofabricated materials we talked about, like mycelium, which are inherently renewable and often biodegradable.
And the sensing capabilities we discussed could even help with maintenance.
Yes, absolutely. Sensors embedded in the furniture could enable proactive maintenance, alerting you or even a service provider to potential issues before they cause a major failure. Some research even looks at self-healing materials that could autonomously repair minor damage, boosting durability even further.
And the fact that it's programmable means it can stay relevant longer, even if my tastes or needs change.
That's a key point for extending the functional life. If furniture can change its form, its texture, maybe even its color via programmable matter interfaces, it can adapt to changing aesthetics or new functional requirements. This tackles that issue of discarding perfectly functional furniture just because it feels outdated or doesn't fit a new use case.
And what about new business models, like furniture as a service?
That comes up too. FAIS or leasing models fundamentally shift the incentives for manufacturers. If they retain ownership of the furniture and you're essentially paying for the service it provides, then they are directly motivated to design for durability, easy repair, and efficient end-of-life recovery and recycling, because that maximizes their asset value. It shifts the focus from just selling units to optimizing the product's entire life cycle performance.
So pulling it all together, this transition isn't just about adding flashy tech to chairs and tables. It's about creating objects that are inherently more adaptable, much longer lasting, and built from the ground up using materials and processes that prioritize keeping resources in use and drastically minimizing waste.
It's a really comprehensive vision, isn't it? It's this convergence of material science, robotics, computation, user interaction design, new manufacturing paradigms, and it's all threaded together by this critical imperative to move towards a genuinely circular, more sustainable future for our built environment.
It really makes you stop and think. If the everyday objects around us, starting with our furniture, can sense our presence, adapt to our needs, subtly influence how we interact, and even change their own form autonomously, what other objects in our lives could be similarly transformed? What are the incredible opportunities, but also the significant challenges of living in a world where the physical environment itself is becoming actively responsive to us?
That's definitely something fascinating to mull over until our next deep dive.